This should be a fantastic class. This should be the one moment, one of those few moments when we are in sync, because for a while here, from the first midterm, you had the first midterm here, and then you had to deal with your other 73 courses, and you've had to drift away. But now, regrettably, unfortunately, your attention is now once again here for Thursday. So hopefully we're getting on the same page. For you all, I wish an epiphany. Now, that could mean various things, but in the mundane world of IEOR, that just means that all this stuff should become clear to you. What unfortunately is the case is there tends to be no halfway. This stuff seems like total, whatever, Greek, unless you're Greek or whatever, to you until you learn it. But once you see what's going on, all of a sudden, it's totally easy. I mean, that's the trouble. I mean, it's sort of, you probably know that already. Once you understand it, the stuff becomes simple. When you don't understand it, it's totally complicated. And if you can make that, transition, you'll be in business. And then the problems don't matter, the variations. Once you've understand the few key concepts, everything falls into place. So what should be happening is that you should be, if not now, between now and Thursday, and if necessary between 11 a.m. and 1 p.m., so Thursday, but between now and 11 to 1 on Thursday, and in the realization will be in that other classroom, 303 downstairs. So we'll do the exam down there. But hopefully this all falls in place. And in some sense, this subject is not all that terrific for the usual mode of studying, right before the exam and ignoring it the rest of the time. The only bad part about that really is that in between, it seems like you're encountering total nonsense, gibberish from the professor. But otherwise, maybe it's fine. You could maybe learn all this stuff in 2 or 3 days and be fine. But now actually you should be, hopefully, you're in great shape if you're halfway there. Meaning if you've already started, then maybe if you started already, then you should be in great shape, and you're in the middle of your epiphany, and what I say will be comprehensible today because you've already started. If you haven't started, then I wish you this in the next 3 days, right, between today, Wednesday, and Thursday, so you could probably do it then too. So since the focus is pretty narrow, the challenge isn't too crazy. It's not crazy that you could sit down and start today from scratch and learn 2 chapters. So it's not really that hard, and once you learn it, it's easy, but until you do it, it's totally impossible. Okay, so then I'm actually trying to think of sort of not to waste your time in this. This looks like this is my plan. Looks like frivolous, and I'm not being concerned about your epiphany, that you should reach your epiphany. But these 3 problems are sort of chosen to be somewhat hard so that they help you with the parts that you need help with. That was my intent. It doesn't look like it, does it? But anyway, okay. So, and as usual, the things we'll talk about are very tangential to the real issues, but we'll somehow make probability models relate to this. So we're going to want to start by making a probability model of an Easter egg hunt. I mean, okay, it's pretty ridiculous. So there's some park here, and sort of the general idea in this park is that you're hiding some Easter eggs in the park. Okay? And if you did a good job, you would the Easter eggs would be randomly distributed somehow in the park, okay? And if you had a bunch of you and your friends doing this, you each had some eggs and some candy, and you put this stuff all over the place, you think, okay, now you have the Easter eggs are in this park, and then you think about where are they? And, maybe there are some nice places. There are some hedges here and things here and various places in this park that you might be nice to put the Easter eggs and so forth. But anyway, we don't need this part. But you sort of randomly put the Easter eggs in the park, and then you might think that, well, okay, let's think about what maybe there's some eggs in here, and then what the distribution of the eggs would be in various places in the park. And they're randomly there. So a natural model for this would be a Poisson random measure, a Poisson process in this park. So we might have, what we would have here is an intensity function, lambda of t. And lambda of t would be where t is someplace in this park. So you could think of it, t is really a variable in 2 dimensions because it's a place in the park. And the intensity is the likelihood of, and at point t, is the likelihood of an egg being at that point. So maybe it's more likely, some places are more likely to have eggs than others. This would be useful if you were the seeker of the eggs and you wanted to do this in some sort of optimal way. So where are the eggs most likely to be and so forth. And you'd have some intensity of where you think the eggs might be. This is deterministic. So there's a deterministic function over the park, lambda of t, that's giving you the intensity of finding an egg at any point. Now, if this were Poisson, if we made this a Poisson process, there'd be some region of the park, A. A is this. And we would want to know what's the distribution of the number of eggs in A. And everything's determined by this. Okay, that's sort of the Poisson process model, but the Poisson process in this space. So you could call it a Poisson random measure or a Poisson process over the plane. And what is it? So the probability that the number of points in A, we just write this, the number of points in A is k. So very straightforward. Number of points in A is Poisson with a certain mean, and that since it's Poisson, all that matters is the mean. And the question is, how do you treat the mean in relation to this intensity, right? So the Poisson process is going to be a Poisson distribution. There it is, Poisson. The only thing that's missing is the mean, and the mean's going to depend on A. And the obvious thing is that the mean should be the integral of lambda t over A. This integral really is a 2-dimensional integral over the plane. Right? That's the mean. The overall mean is the integral of the intensity over this set. Now, the important Poisson property is this. If we had another region B, the same thing would be true, but we would have the integral of lambda over B. But the Poisson property is that for 2 disjoint regions, the number of points in the disjoint regions will be independent. That's where the Poisson, the stronger property. The number of points in A and B for any 2 sets that are disjoint, the number of points in those sets are independent. So if I made something like this, and I wanted to know about A and B here, I would actually divide it into this piece, and this one, right? And then I'd have 3 disjoint sets. And I would integrate lambda separately over those 3. Because I would be counting this part twice. So that's useful to know this story about a Poisson process in a general space. So it's like this distribution of stars in the sky or something. You could be lots of things. Raisins in cookies and so forth could be like this. But this is also what we do in the simplest case. Okay, well that's the end of the Easter egg hunt. It's just that it would be a Poisson process. Okay. Now, the standard case really is the same. So here's time, and here's the standard case. And here's some interval CD. And we want to know the distribution of the number of points here. And if we have a Poisson process with rate lambda, constant, we want to know the number of points in here. We would write the probability that n of t, n of d minus n of c equals k equals e to the minus lambda what we've done here is this is counting the number of points in this interval. So when we subtract these two, we count the number of points in here. And what we're really doing here is the same thing. There's an intensity lambda that's constant. And we really when we get this mean, we've integrated this constant lambda over this interval. It's the same idea. So when we multiply lambda times the length of this interval, it's the same thing as integrating lambda over this interval, right? So it's like integrating over the set A. I integrate the intensity or the rate over the set. In this case, it's just over an interval, one-dimensional interval. So lambda is constant. This parameter here times lambda, I could have written m equals the integral from c to d of lambda dt. And that'll be lambda times d minus c. I just want to emphasize that in the standard Poisson process, the mean is lambda times t, the length of the interval. The length of the interval is d minus c. So this is the t that appears here, is this length. Okay, and so the only point I'm making is when you first learn the Poisson process, you know that the mean is lambda t, where t is the length of the interval and lambda is the intensity. And this is just saying that more generally, the intensity might not be constant, so you integrate the intensity over the interval or over the set or whatever you're talking about. Okay? So then we have this, and this is just to say what you know already pretty well, probably the Poisson process with intensity lambda, and you say the mean is lambda t. That's true when the interval's of length t. And it corresponds to integrating lambda over the interval. But lambda is constant, so it's just this. Okay, now we want to go on. And this is background. I guess really the problem I want to consider is number 2. So Easter egg hunt is Poisson process in the plane. Planning the party, we're now going to plan a party. Like we were going to invite all the Ieorertsj students to might be something like this. All undergraduates, master students, all the Ieorertsj students to a party. We're going to have an open house someplace, and we're thinking about how many are, the right thing would be just to get the food, get every liquor, drinks, whatever you're going to have, just make sure you get this. You probably don't think about, when do they arrive? How long are they going to stay? Getting the food at the right time so that if somebody comes toward the end, you want to make sure that they have some fresh hors d'oeuvres, if they come at the end of the party, rather than 4-hour-old, that's probably not too important. But that's what we're going to worry about. So this planning the party is more Poisson process. Just to be clear where we are, it's still a Poisson process. But now I want to talk about, so let me be clear what the focus is. Non-homogeneous Poisson process. This part. It's at the end of chapter 5. And that means lambda is a function of t. And in this case, when I'm thinking of it on the line, so it's less general than in the eggs, right? It's just on the line. And I want to do this mtg infinity q. So this is there's no weighting here, but this is the infinite server Q. And this has, as its arrival process, this. So this is this queuing model that I talked about early on, which was, when I did so, was probably nonsense. And I talked a little bit about last time, maybe also seemed hard. Arrival process is non-homogeneous Poisson, and we have this infinite server queue, and we want to talk about that. And we're going to think of the party in that way. Okay. So this is like one of the problems in the book. So my description of this is, we plan this open house. We're thinking it's going to start at 1. It's going to be for about 4 hours. So we say it's going to start at 1. So we'll put 1, 2, 3, 4, 5. We put 6, 7 here. And this is my idea of, we're planning for the party now, right? So we're going to schedule a party between 1 and 5, 4 hours. So the party, you know, the invitation saying you're invited to this wonderful party for all IUR students. It's going to be between, 1 and 5 p.m. on blah blah date, and so forth. Okay, and then we think, oh, okay, when are people going to arrive? The invitation says this. So now we're going to model when people come to the parties. Well, first of all, we would be much better off probably if this was between 1 and 5 a.m., right? Okay, we do better. Okay, some of you do better. You wouldn't have that. Some of us would not be there to greet you, but we'd do better. Okay, but let's say few people don't arrive early too much. So maybe they arrive. Here's my story of what they arrive like. Now, this is maybe not quite right, but I'm making this just approximately this. So at the beginning, there are not too many people, and then sort of there's some period they arrive, and then they stop arriving so much, and maybe they quit arriving at the end. But some people, maybe a few people, arrive right at the end. Okay, now, actually the party's scheduled between 1 and 5, but people don't pay any attention to that, and so that's certainly a good thing to think about. If you're planning a party and you're going to have, say, thinking of about 100 guests, just for example. Let's have 100 guests. We'll think of 100 guests roughly. I don't know, I think that would be an underestimate. So we think, well, of all these students, we think 100 will come. We have more than that, so that's not very many. But between 1 and 5. So we have this, let me sort of put some units here. So so what I'm plotting here is lambda of t. This is the arrival rate function, the arrival rate for a non. We're going to model, unfortunately, this party degenerates into that we model the arrival of party goers, people coming to our party, as arriving according to a non-homogeneous Poisson process with this rate. At the beginning, they're invited at 1, they start coming at 1, they kind of come more, and then they arrive at peak in here, and then that sort of trails off and they arrive less later. Okay, so that's the arrival process. Now, actually, people, they're not going to leave here unless you kind of, some people are going to be here, so unless you kick them out, right? People are going to, for some crazy reason, people are going to, if you schedule a party between 1 and 5, they're going to dribble out at the end of, they'll be there, some people will be there at 7 o'clock. Even if it was an IEOR party, right? Okay, whatever, it would be like that. So they might be here. So maybe one model, a simple model, is that the times that they stay, well, IID, exponential, mean 2 hours, say. So everybody's independent. They each stay there. The amount of time they spend here is independent and identically distributed exponential random variable with mean 2 hours. So, if you come at 2, your expected time, wherever you come, your expected length of time is 2 hours. But maybe it's exponential, totally random. So maybe somebody's going to stay 10 hours, right? If you let them. So maybe they would just go on, and maybe they wouldn't live. So this person who arrived at 5, you can expect they're going to be there. You expect them to be there around till 7. These few in here are going to be here and here. So you're going to have a few in here. Okay, this part is what we need here. This arrival process with this lambda of t, remember it's a Poisson process, so it's the fully specified by this intensity, lambda of t. That's all you need for the Poisson process. For this part, you need the Poisson process and the service time distribution, and we've said the service times are all independent and identically distributed, exponential with mean 2 hours. So we've now specified this model. If you were asked to specify the model somehow, you would specify, you would construct lambda t like this, and you would specify, make some assumptions like I just did. Okay, so let's make sure that we understand something, what this is saying, what this model is saying. So for this non-homogeneous Poisson, you want to know something like, what's the probability that the number of arrivals, let's call this arrivals, well, n is all right, number of arrivals by, say, between 4 and 3. Well, let's start with the expected number of arrivals between 4 and 3. Where I'm using this again means the 0, 4, and this means 0, 3. Number of arrivals in this interval minus number of arrivals, and this is the number of arrivals in the interval between 3 and 4. So we're looking at this. And then this is going to be something, and then we're going to have the probability that this number is k. Now the point is, this is going to be some m, let's say, and we know this is going to be this. When we want the probability distribution, it's Poisson with some mean, so when we calculate the mean, we're getting the missing parameter, right? All we really need is the mean. We've assumed this is a Poisson process with this intensity. Every random, the number of arrivals in each of these intervals is Poisson with some mean. We just need to calculate the mean. So the answer is always this for some m, where this is going to be the m in this case. It's going to depend on the 3, 4, right? Okay. So what is m? M, in this case, between 3 and 4 lambda t dt, right? We want to know the number of arrivals in this interval. The mean is the integral of the intensity over this interval, right? That's the concept. So it's all you're doing every time. That the mean in the interval is the integral of the intensity. The intensity is the rate. The mean is the integral of this rate. So this is exactly the thing you need to do to go from lambda of t to the mean. Is just integrate this lambda of t here, right? That's all there is to it. All the problems are the same. So here, you're integrating this. Well, okay, so this is a triangle, and so this is 40, this is 20, in the middle is 30, this is length 1, so the mean in here is 30. I mean, you could write the thing out. Okay, what's the mean is the area under the curve. The integral is the area under the curve. It's easy for triangles to say, well, the area under the curve here is 30, because it's 1 times 30, and this part, and this part cancel, right? So this is 30. So if you look at this, at the areas in the hours, you can see right away that in this hour, the rate is 40 times 1. The expected number in this hour is 40. The expected number in this hour is 20. The expected number in this hour is 30 and 10. And indeed, 40, 80, 20, the expected number total is 100. So in this model, we expect 100 customers, customers. We expect party goers, 100. 20, 40, 30, 10 in this shape. And in each case, all I've done to get these numbers is integrate these linear pieces over the interval. And the intervals are all of length 1, so it's just easy, right? So this will turn out to be 30. The expected number between 3 and 4 is 30, and that's just the integral of this, which is going from 40 to 20 over this interval. Okay? Any questions? Yeah.
So, just to kind of check that you're doing things right, you can just kind of solve like make up lambda t, like you can make.
Well, so lambda t was lambda t was critical in the model. I mean, that I was just an assumption that it's this form, and I actually made up the thing so it would be 100. I said 100, so.
So in this case, like in the interval from 3 to 5, you can say like lambda t is like 40 minus 20.
Yeah, you would say this is 40 minus. Yeah, you'd say 40. Yeah, you're right. You're thinking about what, if you write what is lambda of t here, right? It's actually kind of harder to write down than it is to, okay, so 40, what is it? Minus t minus t minus 3, right? Let's think of that. So if we think of t this way, and then it's going down at slope 20, right?
Yeah.
So should I put this? When t is 5, no, I should put it here, shouldn't I? Let's see. So when t is 5, I get 2. Yeah. So this is all right because I just checked that it's right here. Okay, I'm struggling to write down this. So this is 40, and then it would be, it would actually be 60, right? So it would actually, if I put this together, I'd get 100 minus 20t, which is nice clean form for this function right here, is 100 minus 20t, where it would start off at 40, right? This is just what you said. This is exactly what it would be if you're doing the thing mechanically, reasonably. And you think, well, I mean, it's sort of easier to do it just looking at it, right, to eyeballing it. And it's sort of key. But this is exactly right. You would actually make lambda of t. When you said, well, what is lambda t to plug in here? Lambda t is 100 minus 20t for 3 less than t less than or equal to 5. So we just found it. Yeah, that's exactly what you would need to do. That part indeed could be the hard part, right? This is not calculus 1 or 3 or 4 or 1, but still could be the hard part. Agreed. Because you see, I'm struggling, right? Get this right. But fundamentally, I'm finding the area under the curve. So conceptually, so then you, indeed, part of the problem would be here, right? Part of the problem would be that even if you have the epiphany and you've got the stuff cold, you've got to be able to figure out things like, what is this function? Just your point, yeah.
Find all the 3 lines. And you can
from here, you could do between 3 and 4, right? So if we did this, we would, let's just think if we plug this in, we would have, right? We would do this and we would see, oh, that's 100t minus 10t squared, boom, 4, 3, right? And we'd get it.
The thing I was going to say,
okay.
It's much easier to use lambda t with the numbers to calculate the mean overall from 1 to 5 than just eyeball. Because to eyeball the entire thing would be hard.
Well, okay, maybe I'm thinking, okay, 40 here, 20, this is half, this is 40, this thing, this is between 20 and 40. Okay, I mean, I guess I'm actually myself better at just kind of, boom, what the answer is rather than being mechanical, but there's nothing, no, you've got to be able to do that. I can do it too if I'm under pressure, but I'm not so good at it. Okay, go ahead, this is good.
My question would be like, for the interval 1 to 5, right?
Yeah. So you would indeed break this up into pieces, right? Because you couldn't write it all down in some nice way, in this case. You kind of have to do it in the 1, 2, 3 pieces, right? Because it changes shape. You can't actually write down one nice simple function that covers all 3 pieces. So it's messy. So you have to break it up into pieces. And once you break it up into pieces, it's linear, and you could do that by inspection. That's kind of my thought. You actually can't shortcut you can't end up having the whole function look just this simple, no matter what you do, right? So it's going to be sort of messy anyway. The questions are always good. The point is, and the point you should realize is, yeah, the hard part could be this little bit at the end, which is, right? It requires you to think clearly about pre-calculus, right? But it's okay. It's a little struggle. But conceptually, right, you say the integral, but there's a step to go from writing this down to actually doing it. But if you know this theory stuff and you've had your epiphany and you know it's all this, you can do it. If you know that this is all that's left to you to integrate this linear, piecewise linear thing, you can do it. Point is, you'll then, if you're confident you know this is what I got to do, you'll be able to do it. It's the rest of the stuff, if you don't see it, that I think that's what my, right? I mean, if you're confident that's all you got to do, you'd be in business. Okay, this part is only to say, what does this mean? I'm trying to emphasize what is a non-homogeneous Poisson. The number in any interval is Poisson with the integral of the rate as the mean. And then we just discussed how you'd compute that integral in a typical case. Yeah.
That would be a non-homogeneous arrival. It's reasonable to think that the service time, so to speak, may also be non-homogeneous.
Yeah. My model, it's reasonable to think that service times would be non-homogeneous. And I started to make up a model, which is not hard to do, but I didn't want to there's a tendency to go crazy. So my initial model was that actually the departure times would be uniformly distributed between your arrival time and, say, 7 o'clock. And they could be actually time dependent, and you can just stick that in here. But of course, that makes the formula, when you look at the mean formula in the infinite server queue, that the service time distribution is now time dependent as well. You just stick the right thing in. So actually, you can do it with no trouble. But it's messier. It's messier than the straightaway. We're coming to that. So when we come to the infinite server queue, if the service time was time dependent, it would be more complicated. But you could do it. It's just you just do the same thing. It would not differ greatly. It's just a little more mess. Okay, conceptually it's the same thing. Okay, let's think about, we're now going to move to the infinite server queue. So now we sort of know this is the distribution that's describing the distribution of arrivals. In fact, this is the mean number of arrivals in each of these hours, these numbers. But we want to know now, when people arrive, they're going to stay there an exponential length of time with mean 2 hours. So actually, the arrival peaks here, but the number in the system is going to peak later because these people are going to stay a couple hours. So the peak of the real thing, of the shape of the thing, is going to peak somewhere in here. And then there's going to be still people here. So when you look at the expected number here, it's going to be different than this. And it's going to be shifted to the right. Okay, just as intuition, this is describing how people arrive, and then each person who arrives stays in exponential length of time with a mean 2 hours. So it'll be, who's there is going to be shifted to the right by about 2 hours. And I made them all the same to keep it simple, that everybody's staying an exponential length of time with mean 2 hours. Now, the high-level view, the high-level view is to know the punchline. I mean, I'm not going to ask you to prove anything, but you should know the punchline. So the punchline is, if we think of, if I use Q of t as number there, just to make sure it's different from before, number there at time t. The number of people at the party at time t. They arrive this way and they stay that way. You want to know the punchline. The punchline is got two parts. Part one is its Poisson. Part two is there's a formula for the mean. Right? That's sort of like somewhere in there, in various places, in Ross and in my paper, are proofs. But you can just know that. Now, this isn't to say, don't be confused. This is not to say that this is a Poisson process. The number there in different times and so forth are not going to be independent. It's just at any one time, this has a Poisson distribution with some mean. So the fact the number of people at the party at any time is not going to be a Poisson process. It just has a Poisson distribution for each time. And that's a fact that I'm at this point I'm saying, well, that's a wonderful thing that happens here. Just know that. Write it down on your piece of paper. As far as this, you know that. I'm not, there's explanation in the book and in my paper, but you don't need to know that. But that'll make you happier. If you see the proof, it'll make you happier and more comfortable, but we're not worried about proving that. But you want to know, therefore, that this is Poisson and there's a formula for the mean. And the formula, you write it down someplace. Either you know where it is in the book or you know this. So this you know and this you know. You don't have to remember why it's, we'll go into what it is, though, in a second. But at time t, you're going to see oh no, isn't it sort of like this? Yeah, sort of, right? Yeah, okay. Well, let's see. Okay. I mean, you'll have your version, whatever version you have. But let's discuss that guy a little bit. We can do it here. Okay, this picture, I like this picture. Ross doesn't use this picture, but it's in my paper, and I've done this picture. I'm always doing this picture. So what I'm thinking of is I'm plotting the arrivals and service times, and I'm thinking about who's there. So the arrivals before t are occurring according to a rate function, lambda of s up to t, right? So there's a non-homogeneous Poisson process with this time-dependent rate that's a function of s up to time t. I'm interested in who's there. And then they have service times. And because everybody enters service immediately when they arrive, if this is their service time, the amount of time they spend in the system goes down at slope. What's at the end of a 45-degree line, they will be gone. So the points, the service times that fall in this triangle are still there. The ones that fall below the triangle arrived and have left before here. So the important point is the ones that are there, Q of t is the number of points in here. And the departures by t is the number of points down here. Number there, number departed. That's always true without any Poisson assumption. I've just drawn a picture of typical arrivals, typical service times. Of course, these aren't given. This is a possible realization of a random process. Some sort of arrivals occurred in the past, and they each have some sort of service times. The arrival process is Poisson, non-homogeneous Poisson. The service times are independent and identically distributed, assumed to be exponential with mean 2. But this is a possible realization, this picture. So there are 2 points in this picture here. But of course, in general, it's a random number. And there's 1, 2, 3, 4 points over here in this picture, but it's a random number, in fact, because this is just one realization. Now, this is where the Easter egg hunt comes back. Because this is Poisson, and because these are independent and identically distributed, whether this point is here or here is thinning this Poisson process into the ones that are up here and the ones that are down here. So these are both independent Poisson. This is just like the Easter egg. This set here, this triangle is independent, disjoint from this triangle. The number of points in sets in this region is a Poisson process. So this is Poisson and this is Poisson, and the sets are disjoint, so they're independent of each other. Yeah?
I have a quick question about that formula, because I think I understand where it comes from the book, but like in the book it says that the mean would be, I know that lambda changes over time in this one, but it says that it's going to be lambda times the integral from 0 to
Yeah, so if lambda is constant, it will be just the case outside.
But when you find lambda, I would imagine you have to do a separate integral. I didn't know that if you had the integral of 0 to t of lambda s times the integral of that function over there, that you could put...
Well, let's see in the picture what we're doing. So there's 2 parts of this story in this picture. And I want to focus on them both. One part is, this is actually now contrary to what I said before. Before I said, well, you should just know it. I don't want to take that back, but now I'm actually explaining it. But I'm explaining it mostly not to prove the Poisson part, which I'm doing, but to get to your point of why is this the right formula. That's what I'm really interested in here. And so I'm interested in that, but then I'm first saying that, well, this is Poisson and this is Poisson, and they're independent of each other. So that's interesting. If I want to know the number there, Poisson. If I want to know the number of departures, Poisson. And I want the integral of this thing, the intensity here, to be the mean of this, and the integral of the intensity here to be the mean of that. So that, the integral of the intensity, now the intensity in that region at some point would be this, where this is a point at the point S, which is less than t, so, and then here is a height v. So the intensity of a point right here would be the arrival rate at that prime times the probability density function. And in order to integrate this triangle, I would actually have a two-dimensional integral. When I do the integral this way first, I'm integrating the service time distribution should be up here, above this. So if this is S and this is T minus S, this is T minus S. So the service time distribution should be above T minus S. So I've now made it a one, once I do one of the integrals, it's up here. So I've got just one integral now because it was this point was this intensity here, but I've integrated on V first, and I integrate right up here. So now I've only got one integral left. I've got the integral on S. I've actually got a two-dimensional integral. I've got an intensity at a point, and I did one-dimensional integral already to go this way. In other words, this thing, I've got this from, this is dV, ds. S goes from 0 to t. V goes from t minus s to t. T minus s to infinity. And when I do this, I get this. This is really a two-dimensional integral to integrate the intensity over this triangle. And I reduce it to 1 by doing one integral. Conceptually, number of points here, Poisson, number of points here, Poisson, they're independent of each other. Then you just need to know the mean formulas. And now that's, the mean formula is the rate here, lambda of s, times this probability that you're above this point, which is this. Okay. Now, if we continue, we want to stick this in. This is the tail of the CDF. This is this. Because it's exponential, right? We assumed the service time was exponential. This is the tail. So it's got the exponential, and actually 1 over mu is 2, so mu is 1/2, right? Because the mean is 2 hours, so mu is 1/2 in here. So we should really have stick in a half. So then we've actually got this formula. This is what we would want to do. We would now want to do, let's see, what if they're there at t, if we do it 4, we've got to take this exact function and do it in pieces. Okay, this is like the same thing before, and now, for sure, you're going to want the pieces, because you're not going to know what to do with this if you don't have the thing in closed form. However, if you wrote this down, you could stop there. If it's now arithmetic, that's not too bad. In other words, you could say this is the answer, this, and move on. And then save arithmetic to the very end. You could just stop here. This is pretty good. If you have this right, I mean, then, if you're working it out, you're doing that part. This course is primarily not testing that. Primarily not testing that you can do this. When you're left with, in this case, if it was number at 4, you would have had 0 to 4 lambda s e to the minus 1/2 t minus s ds. If we go to to 4 was our case, right? If we wanted to know the number right here, how many are there at time 4, we would do this integral entire past, but might as well be here, start at 1 for that matter, right? It would be just as well to be at 1. And if you did that, you would write down 1 piece, 2 piece, 3 pieces for lambda. And then you'd have the explicit functions just like this piece here, and you do it the 3 pieces. But if you stop there, you're mostly okay. That's not what's being, the intent is not that to test your calculus so much, is to be able to get there. So the main point is actually getting here is pretty good. Okay, it's not emphasized. I'm not really emphasizing that you do that anyway, right? So that in part, if you understand it, the hardest part will be the arithmetic or manipulation at the end, and that's not what we're really testing. So if you get here, this is pretty good. The most you should lose for such a thing would be 1 point. If somehow you wanted to give credit for somebody who had done the whole thing carefully. So don't overemphasize that. Okay. Let's see. So this picture, to emphasize these 2 points, I guess this is always the point. 1 point is this structural thing that the number there at time t is Poisson, the number of departures up to that time is Poisson, and they're independent of each other because it's Poisson. Yeah.
Is n of t always going to equal qt plus qt?
Yeah, that's a good one. So obviously, the number of arrivals, whatever the model, the number of arrivals has to be the number of people there plus the number who've left. So the sum of these 2 is n of t. So, and they're independent, but they're going to be n of t. So these 2 are going to be independent Poissons. But of course, this is consistent because the sum of 2 independent Poissons is again Poisson with the sum of the means. So then these 2 are going to be Poisson with means that you're going to add up to what? They're going to add up to some 90, right? If we do this, the sum of those 2 means are going to add to 90. That's the check you do. Sum of the means of these are going to be 90. The mean number of arrivals up to 4 is 90. You're going to get some number in Q and some number that have left by just by solving this mess. And the corresponding thing is, so if you solve this, you could get the other one by just subtracting from 90. I mean, rather than doing the other integral. So if we did departures, what would it look like then? If we were to look at this, we would say, well, that's the integral from 0 to 4 lambda s g of t minus s ds, right? Which is just the part below, right? The part below, t minus s, but it's this we're integrating, right? Not the appropriate nodding. This is the ones that have left. I'm just doing, instead of doing above, this is t minus s this way, t minus s this way. Instead of this, I want this. So this is the mean of the departures up to time t. Or this is the expected number of departures by 4. And it's not surprising that if you stick this and you add these, this in one and this in the other, it's going to add to 1. And so this will be just the lambda, right? Your point? If I have this for the, this is expected q of t. 4 would be this, what we had before, and then this would be the departures, and the 2 together, well, the g's would cancel and just be 1. Other questions are, I think, really helping. I mean, they're focusing. So if you have a question, think of something to add here. So I'm thinking this takes care of the infinite server model, non-homogeneous Poisson. All this stuff is that point. That's sort of, this example is they're all like this. This is non-homogeneous Poisson process and the infinite server queue with a non-homogeneous Poisson arrival process. Okay. And it's sort of interesting, when the arrivals look like this, and then the number there is going to have some shape, right? And you can actually, when you calculate, if you plot the expected Q of t, you're going to see some interesting shift of when the people are all there. And you could respond to that somehow, that they're going to be there later than this, and sort of shifted by 2 hours. Yeah?
You get that 1 minus g of t minus s equal to e.
So y is 1 minus gt minus s. So this is e to the minus mu t minus s, and mu is 1/2. Okay, well, this is to write, if I wrote g of t, I would write this, because it's exponential. So if it's 1 minus g, it's the tail, it's just this part. And if it's t minus s, it's just that part. Which is a room for confusion, because there's 3 or 4 steps at once, right? 3 or 4 steps at once. But I'm using this. So indeed, I'm remembering the exponential CDF is this. And then if this is the tail of the exponential, and this is the argument, so tail has this form, and then the argument is t minus s. Okay? Yeah, no, this is good. Every question is worth 10 for the 10 people that aren't asking are going to have the same question. So that's nothing wrong with that question. That's easier than a couple of the other questions, but critical. Okay, absolutely critical. And hopefully, part of the epiphany is this sort of thing. When you go through the homework, once you get it down, it all just goes, yeah, of course. Once you absorb it. I mean, that's, until then, sort of, it's total nonsense, and then it'll become, hopefully, there. Okay. Well, I want to discuss the last problem on last year's second midterm, which seems like it's worth some discussion because it's hard enough. I'm thinking it's hard enough that if you read the solution, you might still be confused. Whereas I'm thinking if you do the first problem, you sure as heck should not be confused, okay? That's a warning. If you read the first problem and you've got the solutions in front of you and you don't understand it, really dig in. You got to start working, because that's a bad sign. But the last problem might be confusing. And you sort of might not get it, the last problem. And that's this. So in this last problem is, you're constructing a communication network, and you have a bunch of cities. And the communication network has links between the cities. But you don't want to put extra links. You want the minimal number of links. You want all the cities connected, but with the fewest links. I mean, you can make thick pipes. So if you want to go from, if you do this, say A, B, C, D, E, F. If you want to go from C to B, you can just as well go this route, and you've only had to put in 2 links, and that's sort of cheap if you could do that. So you can just make it so you have minimal number of links, so you kind of do something like this. And you don't put any extra. There's a solution where you can get along some path of these links from any node to any other node along these links. And if you need, of course, this is, if it was fully connected, you would use each link less. But it might very well be the case that it would be much more efficient to just build the links, the minimal number of links, and not have everything links everywhere. And then there's actually some history to this, right? It's certainly obvious that that's not unreasonable. So the thought would be, well, when you do this, if there are n nodes, it's pretty clear that there has to be n minus 1 links in this way. Of course, there'd be n choose 2 links altogether, possible, because there's n nodes, and each link is connecting 2 nodes. There's n choose 2, so there's n choose 2 equals n times n minus 1 over 2. This is how many links there could be for n nodes, right? How many links? But to make one of these connected networks, where, I mean, not fully connected, but connected in this way, we only need n minus 1 links, because every node is connected to one other, and there are no redundancies, right? You can get to from any pair of nodes in exactly one way. If you want to go from E to B, you have to go this way. If you want to go from D to C, you got to go this way, right? So this is a spanning tree. Now we're sort of we're in optimization a bit, but we're thinking this is one of those things where we're going to think about optimization and investigate the benefits of optimization. So you might think that for what the optimization problem is, every potential link, you're sitting here with n nodes, so the n, you have we have a matrix, A, B, C, D, E, F. A, B, C, D, E, F, and we don't have anything on the diagonal, but we have a cost AB, a cost AC, a cost AD, and a cost BC, and so forth. So we have costs for putting a link from every node to every other node. And then the goal is to construct one of these spanning trees that's the least cost spanning tree. So that's called the minimum cost spanning tree. Okay? That's sort of a nice way that's sort of a standard IEOR thing to do to construct the minimum spanning tree. So there's a greedy algorithm for doing this. And that algorithm does the following thing. It's greedy because you don't think too hard. It's always nice when you just do the obvious and it gets you the right place. So you look here in this thing and you find the best link in the whole darn thing, the cheapest one, and you put that in. Right? So you find one of these and you see, oh, it's between C and D. Boom, cheapest one, you put it in. Well, now you consider all the remaining links and all the remaining nodes, all the remaining nodes besides these two, and you could put a link connect to C, or you could connect a link to D from all the remaining nodes. So you look at all the other nodes and you consider all the nodes that connect to C and all the nodes that connect to D, and all those links. So there's 2 nodes are removed, so there's n minus 2 nodes. For the n minus 2 nodes, there's n minus 2 links to C and n minus 2 links to D. So there's 2 times n minus 2 links to consider. You choose the cheapest one. Maybe this is A. This is the cheapest, so this was the minimum. And then of those left, this was the minimum. And you continue in that way every step, one step at a time. You now have 3 of them here, and you say, oh, well, I've got 3. Now I've got n minus 3 remaining nodes, and I consider that they could connect to these 3. And of the available links that connect to one of these 3, I choose the one that has the minimum cost. And I just keep going, and I put the n minus 1 links down. That's the minimum spanning tree. And that's got great properties. That simple thing works great. You may have already proved that in previous course. Okay, now the probability enters in as you think, well, is there any point in that? What if is there any advantage to doing that? Let's just suppose we did at random. How much are we going to benefit from doing that minimum spanning tree from just picking them at random, any old links, as long as it fits? So the issue is, let's make a model that might describe what's going on. So the model is contrived like the thing of studying linear programming, but it sort of gives you an idea of what's going on. You assume that all these costs, they're whatever they are in reality, but we assume that they're independent and identically distributed exponential random variables. Okay, that's total fiction. But you just say, well, let's suppose that's the case, that they're exponential random variables with some unit, like $100 million times the exponential random variable, right? So each link is $100 million times whatever that exponential, like a unit exponential. So there's mean is 100 million, and variance is the square of that, okay? Okay, so that's the cost of each of these. And now you think, well, let's do the minimum one and the random one. So they're both going to produce n minus 1 arcs, and they're both going to produce a spanning tree, but one's the minimum spanning tree, and the other is the random spanning tree, right? And so the random spanning tree is you just pick any old link, and you proceed to add any other link, and you keep going, right? Okay, now if we just forget the $100 million, which is the part that's there to get your attention, right, that it matters, as opposed to it was 10 cents for each one and an exponential multiple, right? So the 100 million's there to get your attention. Maybe you need today we might need 100 billion. I don't know what you need to get your attention. Okay, so we're going to do this thinking of it just the exponential random variables have mean 1. So if you do this totally at random, you proceed randomly. I pick some link, it happens to be this one, and I add one of the other links that connect to these, but at random. I don't minimize anything. Then every time you've done nothing to affect the distributions of the random variables because you haven't looked at the random variables. So actually at each step your exponential random variable always has mean 1. Every one you add, because you haven't done anything to look at them. You just add them randomly. So the mean with that random, the mean cost with the random spanning tree is n minus 1. 1 for each one, n minus 1 links, 1, in whatever units. This is this. So the question would be, let's suppose we do the minimum spanning tree. How much better are we going to do? Now we're going to use, of course, this is where the part of the course comes in. All these link costs are independent exponential random variables. So now we're going to use chapter 5 heavily, right? We're going to exploit chapter 5. We better do so quickly so that what we want to do this. So we're now going to do the minimum spanning tree. And this part is the part where I think everything up to now is totally obvious too, or at least would be clear if you're sitting down and reading it. But this is the part where it gets tricky. Now you're going to do the minimum spanning. So in fact, all these exponential costs are generated. They're independent, identically distributed exponential random variables with mean 1, but they're generated. So when you do the minimum, you're going to look at them and somehow select them. First one you select is going to be the minimum. And then you're going to look at the remainder. Okay, so that's what you want to think about. So in the beginning, there are n choose 2 equals n times n minus 1 over 2, this many links. So when you pick the first link, you're choosing the minimum of this many exponential random variables. Remember, so this is perhaps the key thought in chapter 5, is that when you look at minimum of independent exponential random variables, the rate is the sum of the rates. You use that in continuous time Markov chains when you're thinking, I have 3 things that can happen. The time at which it happens is going to be the sum of the rates. So this is really critical. So when I do a minimum, the expected cost of link 1, the first link I put down, is this. It's the mean, the rate is the sum of the rates. So this is the rate, the reciprocal is the mean. You see, you're already in business. So the first link, instead of costing 1, costs this 1 over n squared like thing. So it's looking really good, right? You're just the random things, you're actually going to pick small ones, right? Now, this part is also not too hard. It's the next step that's critical that you might miss. It's the very next, and maybe the next step is the hard part. You've looked at these links, and you picked the minimum of all these exponential random variables. Yeah, go ahead.
Are the exponential of the mean 1 or?
Yeah, each random variables mean 1. I'm forgetting the 100 million for the moment, right? Okay, so we forget the 100 million. Each one is mean 1. Now, this is actually written in the solutions of the, this is the last problem on last year's second midterm, but, and the solution's written there, but it's this next step that the one that you might say, I don't get it, okay? You got right here, this looks pretty clear, it's the next step. You've looked at all the random variables and you picked the minimum. So, you've got these other random variables. Now things are getting confusing. Because you've looked at them all already, you got a problem. What's independent? I mean, you got a problem. You looked at them all. Whatever they were, you looked at them and you picked the minimum. So you've seen them all. Now you've got next, the next link. There's n minus 2 nodes available. Each could connect to 2 of the nodes, right? So you've got 2 times n minus 2 links. Next to consider. I mean, you've picked the minimum, you picked the best one, and there's 2 nodes, and there's n minus 2 other nodes left. Each of those n minus 2 could connect to the individual first 2 nodes on the link, right? So this is how many links you've got to consider next. And we're just coming to the point. But you've already looked at those links, and you've seen that their cost is greater than the first one. So, I mean, it's a lot of, things aren't right yet. So now this is the critical point, right? Right, absolutely now. Okay, so there are this many new links to consider. Here's the point. At this point, all their values are greater than this first cost, whatever it was, right? And the amount greater has the lack of memory property. So conditioned on they're all greater than this first cost, whatever it was, they are independent random variables, exponential 1 again. Because lack of memory property, even though you looked at them, you're only conditioning on they're greater than that minimal cost. They have costs that are greater than the minimum cost, but the amount greater is yet to be determined and is independent exponential with the same distribution. So actually at this second stage, you're looking at 2n minus 2 exponential, IID exponential. But now this is another subtle point. This is what's additional. Because all those costs have this first cost as given. So there's an expected first cost is this. So the next one is going to be 2n minus 1 plus 1 over 2 n minus 2. This is the first part because all those other costs are the first cost plus whatever is extra. And the extra has the lack of memory. This is where it's getting tricky, right? So the first thing was clear enough, just straight minimum. But when you get here and you're considering these next 2n minus 2 links, you want to realize it's the extra part above the first cost. So they all have the first cost over again. They have this piece, plus they're going to be the minimum of these. So the cost is going to be the first exponential cost plus the second, and the second's going to be the minimum of this many exponentials. That part, this step is the key part. That you understand that when you go to the second one, well, yeah, I've looked at them all, but it's the leftover pieces, and so I've got to include this again down here for this cost for the second one. The first cost plus the leftover. And then the same idea repeats. When you consider the third link, you've got to add the first 2 expected costs plus the leftover again. But once you've seen this, you'll understand, once you've seen this, you will understand the solutions. I'm just saying the solutions might not make sense if you didn't see this. It's written, this is all written, the solutions are written there, but you might not believe this. This thing here would look like you just might not get it. Because you have to think, oh, sure, this is the minimum of this many exponentials, therefore it'll have this mean. But when you go to the next step, you got to realize I'm going to be looking at this many links, and their cost has an expected value equal to the cost of the first one plus what's left over, and the left over are these minimum of these, and their IID again. It's an amazing property of the exponential distribution, getting you all this stuff tractable. Simple answer. So when you carry all this stuff out, then you see that the formula will ultimately simplify because this first cost is going to appear every time because it's always added. And then this one's going to appear, all of them after this one, and so forth. So that you're going to end up with a formula. I mean, the arithmetic is there, but you end up with this is this, and here it sort of looks, I guess the answer is which is almost, it's almost this. So this looks like let me write this. This part is not too important. This is just the arithmetic at the end. When you do all of that stuff, you're going to get an answer that looks like this. And then you'll see this is just the sum of these reciprocals of integers, except you don't have the 1, and you have an extra 1 over n. So you have this. You have sum of reciprocals. That is supposed to be, this would be, could be, might be something that really rings a bell with you. This thing is asymptotically log n. This comes up a lot in math. This combination, things like sums of reciprocals. This thing, as n gets big, this approaches log n. So what you're seeing here, the bottom line is that from this model, a random spanning tree is expected cost is order n, n minus 1, whereas this minimal spanning tree, its expected cost is log n. So it's really much, much better. So from this point of view, you could see right away that a minimal spanning tree is much better than a random spanning tree, which you would probably expect. But it actually kind of quantifies it in this context of log n and n, which is probably roughly right for that's probably roughly right for a lot of problems of what you're gaining, which is huge, right? So it's sort of, yeah, this optimization would be worth doing. But the part about this problem that's crucial is you're seeing how to use the exponential distribution, that the minimum of exponentials, again, exponential and so forth, and lack of memory property and all that stuff. So if you understand this well, this problem, probably all the other problems, of which some you will see, will be similar. Okay? Okay. Good luck in reaching this by Thursday. I hope you do.